Hey YouTube, I'm hoping this will work out. I'm trying to, I'm in the old junk room, and I'm trying to put something together here. I don't know how well this can be seen from the computer. Yeah, it looks pretty good. Alright, the reason I'm doing this tonight is because I've been involved in racing and race engines and stuff for a very long time. One of my teachers, 1960, he had the Harley Davidson drag racing record. He was in the tens, and he did it with a Native American. The guy was pretty cool. It was before my time. I was born in '74. I was taught about sodium-filled valves, about all sorts of stuff. You have, but you know, it's like anything else. You have to do your work. You have to go and do your work. And I've read books and books and books, and it's funny. Some books take 1,000 pages to make analogies. Like in Christianity, there's analogies in the Bible, metaphors, analogies, and some men actually did that in the 30s, 40s, 50s, 60s. Actually, 30s and 40s and 50s were about it. These men, they knew how the motor worked. In 1956, Ed Iskandarian milked a lot of horsepower out of an engine. But anyway, you ask some people how an engine works, and they know that an engine it can't run on too much gas mixed with the air, can't run on too little gas mixed with the air. They know the temperature changes. If it's 110 degrees out, you have to mix less gas to make horsepower. If you're in Alaska and it's like 5 below zero, you have to use so much more gas. And that's like starting an engine. They used to use a choke to start the engine with extra gas. Well, it's kind of amazing because sometimes guys don't realize that continues on, that extends on, that process as the fire kicks up. As the temperature increases, you need less oxygen to keep the fire burning. Now, where we're at right here, I'm hoping this comes through good. I really am, because you know it's funny sometimes. You listen to guys talk about their engines, and I've been involved in all sorts of records and stuff. And very, very familiar with all the cutting edge stuff and fuel additives and the chemistry of stuff. But I'm going to go ahead, and that spark plug has just arced. I hope this comes through. But there's spark. Now we'll go back. This is the beginning of explosions in engines. There's no spark. Now there's a spark. Now you go a few frames ahead, and it's sparking and sparking and sparking. There's nothing you see, but it's on fire. The reason you know it's on fire is because a few more frames, sparking and sparking, you begin to see, after a few more frames ahead while it's sparking and sparking, off in the corner there, they're called kernels. They show up far away from the spark plug spark. They're called kernels because they look like kernels of corn. And as you advance and advance, you see one kernel, another kernel, the spark plug's still sparking. Actually, no, the spark plug is long since gone out now. The reason you can't see any flame in this is because you're burning freed hydrogen. Hydrogen can burn hot, it can burn cool, it releases some water, some vapor, but the thing about hydrogen is it burns without a visible flame. The hydrogen burns clear. Okay? It's a colorless, pure hydrogen, it burns colorless. So let's go back here to where, okay, these are the last frames of the spark plug sparking. Now we're several frames ahead. The spark plug is done. Wait, hold on. Now the spark plug is done. There's nothing. Hydrogen is burning. Burning, burning, burning. You continue on a little bit further. Actually, no, I'm sorry, the spark plug is still going. You continue on and you see more kernels. We're back to where we were with the spark plug. You can see more kernels burning, and all of a sudden, you see everywhere, there's kernels, and everything's getting blue. The kernels are hydrocarbon. The earliest burning of hydrocarbon amidst the burning of freed hydrogen. You go a little further, and there's kernels everywhere, and there's a milky blue. You see the kernels shooting down. They're getting a little bit bigger. And now everything is reddish, yellowish. And we go a little bit ahead, and now it's starting to turn blue. Okay, it's turning blue because the hydrogen that was burning, which burns clear, is now giving way to the burning of hydrocarbons. They're denser. It's a totally different kind of burn. But the hydrocarbons are kicking in now, and it's blue. See, it's blue. It's blue. The kernels have kind of disappeared now. Now it's really blue. It's a couple thousand degrees. But there's something that's happening here, and it's called heat rejection. Heat rejection is that most of the air in there is much cooler than the flame. All the nitrogen in there is much cooler than the blue flame, although the blue flame looks to be everywhere. But the thing is, heat rejection is the air closest to the flame expands and reacts violently, while the air further back from the actual burning molecules is isolated from the flame. Now what you have is, suddenly all the blues went out. Blues, and they went out. Now you might say, why'd they go out and get replaced with kernels? The kernels are hydrocarbons burning somewhat rich, little bits of hydrocarbon here and there. What happens is, when gas gets hot, it gets thick, like oil or honey in the freezer, or if you put syrup in the freezer, it'll get real thick. Air does the opposite when it gets hot. So the air is really, really hot, and air gets thicker or viscous when it gets hot. Now all the air near the hydrocarbon burning, has gotten hot. It's viscous. It won't supply the oxygen to the flame. And suddenly the flame went out. Next frame, the flame's starting up again. Each time it starts up again, it's got some heat pent up in the air that wasn't burning, the air that was away from the flame. So each time it kicks up again, two things happen. It's easier for the flame to hit a higher temperature, and when it hits that higher temperature, it requires less oxygen to make a higher temperature. Now see, it was blue. Go ahead. Oh, blue went away. There's kernels. A little bit more blue. The oxygen's combining, but then it gets viscous, and the oxygen can't find its way to the molecules that are burning. Oh, well, here we go. Now it kicked in. It kicked in really, really bright. Super bright, in fact. Very clean. No kernels. Next frame. The blue went away, and the kernels are showing up. It got so hot that the oxygen could not find its way to the molecules to keep combining. Next frame. Blue, some kernels. Blue, some more kernels. The nitrogen is taking on heat, and now you're starting to see by the intake valve, it's always cold, a rich burn. That's because the air around the intake valve, even in this early stage, is so cold that it burns rich. It would require more oxygen to make that burn